Okay, guys. Second one of today. This one's pretty short as well. And yeah, it'll be an assignment to do today, tomorrow, whenever you get a chance. It doesn't have to be done today. But it's just more questions. Some of them I thought are pretty good. Pretty kind of like a little brain teasing. Lost all my hair doing it too. So let's do this. Let me share my screen. Get rid of you. Flip you over and turn off my camera so you don't just stare at my shiny skull. Okay. Starting with just a quick reminder of how a transducer is built. Okay, well, I guess we'll start up here. We have a case that's pretty obvious. You hold on to the case. By the way, questions, I think a question that I'm going to skip is, what does the case do? Well, it protects you and the patient from electric shock. Of course, it'd be kind of weird to have an electrical appliance without a case, but it also protects the internal components as well. So that's pretty obvious. The green line here, and I wrote really small, so it's, I use one line for two things. There's an acoustic and an electric shield. The acoustic shield, you don't need sound from the outside world coming in, and electric shield, you don't need electric fields from equipment in the area also coming in and messing with you, because an electric field will induce an electric current, and since we're dealing with unbelievably low currents, it wouldn't take much of a field to induce a current that the computer would see as an echo. So that would be a pain. So a little shielding in there. Of course, we have wire. And if you say your element plus your wire plus the specific electronics in the receiver. Let's see, actually, you know what? Let's put beamformer plus receiver. So everything that is specific to one element, like the wire, the electronics, that is a channel, of course. We have, oh, I forgot to write in this, kind of the more important things. The backing, sometimes called dampening material. And of course, we know that that stops the transducer element, the PZT, from ringing. We don't want it to ring, we want it to click. Oh, I saw an awesome show about sperm whales and how they're being affected by sound in the ocean. But they were able to observe and listen to a sperm whale going 1,500 meters deep. I mean, that's so deep. That is amazing. And they go down there and they stay down there and they hunt, and you could hear them using sound waves to echolocate. And at first it starts kind of slow, click, and it's a click. It's not hey, Dory, you know, it's nothing like that. It's a short click, because they want to make a short pulse, which will produce a short echo, hopefully somewhat in the shape of a squid, because that is what they normally eat, is deep sea squids. Really interesting. I forgot what it was called, but you guys could find it. Anywho, so okay, yeah, we have the backing or the dampening material, the PZT. In this case, I didn't do a single element. I did multiple elements with multiple channels. We have a matching layer. Oh, matching layer. We're gonna cover the thickness of the matching layer in one of our questions anyway, because I was gonna remind you on that. But I drew in two. I did a light, a purple and a blue. And reality is a matching layer is multi-layered because of impedance reasons. Then I threw the gel in here as well. Just remember that with impedance, multiple layers of matching in reality. Edelman only mentions one layer, so that's fine too. You call it one layer, and perhaps it is in many cases, but in other cases, I know for a fact that is sometimes multi-layered matching layer because you want to step down the impedance from very high impedance of the element to the relatively low impedance of our skin and soft tissue. Okay, so that's a very quick review of a transducer. So how thick is the active element of a 3 megahertz pulsed transducer? What? That's number 276. How thick is the element? And the letter A is 1.54 millimeters, B 0.51 millimeters, C half the wavelength of the sound wave in PZT or in the element, 1/4 wavelength of the sound in the matching layer. Okay. So the answer there is, you guys know it, right? 1/2 the wavelength. So remember, I've drawn it out before. I've drawn this out where here's my PZT, and the thickness is all we care about. And 1/2 of the total cycle is still inside of that element because it's still being produced. All right, so that's how it is. I decided for the heck of it, because when I first started reading the question, my kitty cat just showed up. Yes, I know. Where was I here? All right, sorry, distraction. Cats are distracting. When I first started reading this question, I thought they were going to ask what the actual number is, and then I realized that we're missing something from the equation, but I decided to do the equation anyway. So I drew, let's say, this little small triangle here with, you know, this C and frequency and wavelength, and for C, in a typical element, it's 4 to 6 millimeters per microsecond, much faster. We already know that the frequency is 3 megahertz. So what's the wavelength? And therefore, what's half the wavelength eventually, right? If we were going to find a number for this question, which we weren't asked to do, but let's do it anyway. So I have to kind of make a choice somewhere in this speed of sound. And I just chose 4 millimeters per microsecond and 3 on the bottom. So basically I'm finding, I'm sorry, oops. I am finding wavelength. And so I'm doing that part of the equation. So wavelength C over F. And if I use 4, I get 1.3 millimeters is the wavelength. And so if you want to know what the size of that transducer is, 1/2. See that? 1/2 of the wavelength, 1.3 divided by 2, 0.67 millimeters is the thickness. Let me pause here for a second. Okay. 279. Which component of an ultrasound? Yeah, okay. Which component of an ultrasound transducer is made of a slab of epoxy embedded with tungsten particles? This isn't exactly a trick question, so I'm not even sure why I had it in here. But what does that sound like? That sounds like letter C. They say damping, also called backing material. Okay, 280, true or false? What was that question? The characteristic impedance of acoustic gel is greater than the matching layer's impedance, but less than the piezoelectric element's impedance. Okay, let's break this down and think about this without just jumping right into a true or false. Well, the answer is false, so I just jumped in. But why is it false? Okay, so gel is greater than matching layer impedance. Okay, so gel is greater than matching, but less than, gel is greater than matching layer, but less than piezoelectric. So let's see, gel is greater than, but less than PZT. All right. Did I write that right? Less than piezoelectric, greater than matching. Yes, so I wrote that down correctly. What is wrong here, guys? What is wrong? When you're walking down a set of stairs, do you expect the next step to be down or up if you're walking down those stairs? I would fire my carpenter. I'd actually probably beat him with his own hammer if that's a set of stairs that he built for me. No. Stairs, down, 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 right? Not down, down, up, down, down. That doesn't make any sense. What's going on here? It's PZT should be greater than the matching, which is the next thing, which is greater than gel, which, by the way, is greater than skin. See, I was just putting it in order. Now that makes sense. So this is false. 281, I think I might have already just answered. Well, I kind of answered 281. Matching layer, let me read the whole thing. The impedance of the transducer's matching layer is 2.6 megarails, and the impedance of the piezoelectric crystal is 3.4 mega rails. If this is assumed to be a good imaging system, what is the best estimate for the impedance of the skin? Okay. Matching layer is 2.6 in PZT, 3.4. So let's just use what I had up here. I don't have to write this out again. 3.4, 2.6, and what's the question, gel or skin? Skin. So we skip the gel. And we go right to skin. That's fine. The gel's got its own layer. So is it going to be 3.8? Nope. 3.4, 2.8. No, those numbers are akin to having to step up in order to go down. This is down and down. So the next one needs to be, the only correct answer possible is 1.5 megarails. Right? It's just putting things in order. All right. 284, I didn't write anything down. It must be a somewhat straightforward. 284. Yeah. What is the thickness of the matching layer of a 2 megahertz pulsed wave transducer? Matching layer, matching layer, matching layer. There's no trick on this question at all. It's just knowledge. But I want to make sure you guys know this. 1/4 the wavelength of sound. So matching layer or layers, 1/4 wavelength. Whoops. How does that happen? How do I say 1/4 and write 1/2? It's really weird. Anywho, okay, 1/4. I don't know why. I honestly, I don't know why. What's the significance of 1/4 with matching layer? I haven't figured that one out. But something we should probably know. Okay, this guy. Go away. True or false? The backing material helps to decrease the duty cycle at a particular PRF. Duty. Okay. Let's just look at a couple things here. One, duty factor. Really, more or less the same thing. So don't want you to get confused by duty cycle and say, oh my God, it's something completely different than duty factor. No, it's just the same thing. Duty factor and PRF. Well, they're related, but particular PRF backing, the backing material is the backing material, whether it's a high PRF or a low PRF. I think this is actually unnecessary information. The backing material helps to decrease the duty factor. What is the duty cycle or duty factor? It's the time talking, right? Backing material. Without a backing material, your time talking would be a lot longer. With backing material, talk. Okay. Couldn't remember if I had drawn something or not. I hope that makes sense. Backing material helps to decrease the duty cycle at a particular PRF. It's actually a relatively easy question. But one, they threw in unnecessary information. And two, they use duty cycle rather than duty factor. I don't think it's the first time you've seen cycle, but we usually refer to duty factor. Okay, 289, the backing material decreases the quality factor. The backing material decreases the quality. This is true. Quality quite literally means the quality of the sound. You ring a nice bell and you let it ring, it produces a nice sound. But you put your hand around that bell and you ring it and you get an ugly click. So low quality. And by the way, those whales, when they were using echolocation, they were using pretty ugly sounding clicks. There was nothing pretty about it. It was literally a click, like click, 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 click. Actually, it kind of sounded like, and then it would get close, Pulse repetition frequency increased because it was close to its target. Think about that. And it gets really close. And it actually got to the point where I can't even tap fast enough. It's the pulse repetition frequency from the whale increased like that. It was really cool. Really cool. What do I have over here? I forgot. Oh, yes. 291. 291. Oh, I'm gonna have to read this one out. Assume that the frequency of sound with the greatest power emitted by a transducer is 5 megahertz. Okay, that's a long-winded way of saying FO equals 5 megahertz. Operating frequency is 5 megahertz. It's just, you know, it's just a long-winded way of saying it and hoping to trip you up. Let's see. However, the pulse contains acoustic energy with frequency as low at 3.5 and as high as 6.5 megahertz. What is the bandwidth? Okay, well, let's just look at what our bandwidth looks like. So operating frequency, 5 megahertz, and it was as low as 3.5, as high as 6.5. Bandwidth, guys, and I'm just going over this. I feel like I didn't, I feel like I've run into this question before, and I was kind of like, what? So I don't want you to be going, what? So, if this is my bandwidth, this is my width is, well, the width of your sound, the sound that you're producing. And if you want to know what that is, it's just simply 6.5 minus 3.5. Let's just always keep our units here. I have a habit of dropping units. It's actually a really bad habit. Subtract it, because you just want to know what is that. So, 3 megahertz should be the answer. What number is this again? 291. Oh God, please. Yes. Oh, thank God. D. Moving right along. Okay, tricky. Okay, 294 is not terribly tricky. At least I didn't write it down as tricky. Which of the following actions would cause a PCT crystal to lose its special properties? Okay, so I didn't write anything down, but just listen carefully. What would cause a piezoelectric material crystal to lose its special properties? Breaking it into pieces, exposing it to high temperature, exposing it to electric current, exposing it to low pressures. Now, exposing it to electric current is what we do every single time we turn the machine on. So that's not it. Exposing it to low pressures, I mean, what does that even mean? So no, that's not it. High temperatures, guys, remember these are made in the Curie point temperature. And so if you introduce the element to the Curie point temperature again, it's RIP, right? So the answer is B, but the reason I took this question is letter A says breaking it into pieces. That's tricky. Breaking it into pieces renders it useless for us because you've broken the transducer. But even though it's broken into smaller pieces, it's still piezoelectric material. It's useless for us, but that's not what it's asking. It's asking what would crystal to lose its special properties. Its special properties, or it's still, cut an apple in half and it's still an apple, just not a full apple. Okay. I think, is this the last one? Oh, it is not. But 296, tricky. Tricky, yes. Which properties of the piezoelectric crystal of a continuous wave transducer result in the highest emitted acoustic wave frequency? So as we know, guys, we know that thin elements produce higher frequencies than thick elements. Once again, that's just simply a matter of, whoops, well, you know what I'm trying to draw here is that the element's thickness has a lot to do with the wavelength. But that's pulse wave. So let me just give you a quick reminder of pulse wave. So let's draw a little wire going to this, and there's going to be an electric voltage that comes down that wire to stimulate the PZT material to create the sound. If the fundamental frequency is 3 megahertz, the machine, the ultrasound machine, is going to hit it with a voltage tuned to 3 megahertz as well, because it makes sense to try to stimulate the bell with the voltage, the same voltage as the sound wave that's going to be coming out. It just makes it easier. But it doesn't have to be the voltage. That voltage could be 2 megahertz. And a 2 megahertz voltage coming down is still going to stimulate the element, and the element is still going to go at 3 megahertz. Same thing, you could hit it with, gosh, I guess you could hit it with 10 megahertz. It's not efficient, but it's still going to produce a fundamental frequency of 3 megahertz, because what causes the frequency is thickness, for the most part. Thickness and actually speed of sound has a. No, I'm sorry, no, wavelength is thickness, frequency is speed of sound and thickness. Okay, but anyway. So it makes sense to hit it with 3, but you don't have to. Continuous wave transducers have a little more leeway. If you hit it with a 3 megahertz, it creates 3 megahertz. If you hit it with 8 megahertz, it will then create 8 megahertz. Now, what's the difference? The difference is this. This voltage, let's just say, we'll stick with the 8 megahertz. This voltage is continuous. And of course, the sound is continuous as well, but that voltage is continuous. It will continue to vibrate this transducer, this element, at the at whatever frequency the voltage is. That's what the PZT element will vibrate at. That's the sound it will create. So continuous wave transducers, whatever voltage you hit them with is the sound that it creates. I will say, and this is not part of the book, so take this with a grain of salt. You know, you're not going to hit an extremely thick element with an extremely high frequency voltage and vice versa. You're going to hit it with, you know, so there is some tuning involved, but there's a lot more leeway with continuous wave. Back to this guy over here. Just remember, this guy is struck once, quickly, and then allowed to ring on its own. And so that is why the sound, I'm sorry, the wave, you know, the wavelength is created by more the element in pulse wave. Okay. So what's the answer then? What's the question? Which properties of the blah, blah, blah. It says thin, high propagation speed, thick, slow propagation speed, thin, slow propagation speed, none of the above. The actually answer is none of the above. The frequency of sound emitted by a continuous wave transducer is determined only by the frequency of the electrical signal that excites the piezoelectric crystal. So that was tricky. All right. This is almost my last one. Not quite. All right. We're getting there. 299. An ultrasonic pulse is traveling in soft tissue. Which of the following is most important in determination of the frequency of sound? Wow. So I think they're throwing us off here. Let's skip the first line and go, which of the following is most important in determination of the frequency of sound? Propagation speed of the matching layer? No. Thickness, thickness of the backing material. Ooh, wait a minute. No. Backing material, that doesn't make any sense. And go back to A, the matching layer, no. Impedance of the matching, well, that's a double whammy. What does impedance have to do with? No. Propagation speed of the element. Okay, so you look at this question fast and you work your way through it and you just see thickness, there's a chance that you're going to circle B. No, thickness of the backing material has nothing to do with it. But you're like, wait, but Kurt, it's the thickness of the element. You keep telling us it's the thickness of the element that, you know, here's my wave and all that. Yeah, that's kind of like the main gist of it, but it's propagation speed as well. I think, I recall, well, no, I didn't. Okay. C element, frequency operating. And rather than, you know what, I'm going to put lambda over here because in place of lambda, I'm going to write 2 times thickness. 2 times thickness is lambda. Okay. So I want to know that the ultrasound is in the soft tissue, which of the following is most important in determination of the frequency of sound. So I'm going to solve for frequency by using C element divided by 2 times the thickness. They tricked us here. We spent a lot of time talking about the thickness here, not so much time talking about the speed of sound in the element. That's the answer. Propagation speed of the element. All right. I would have jumped straight to thickness if I didn't read this carefully. All right. I said, yikes, something's up here. 302, what's the whole question? You are asked to fabricate a pulsed ultrasound transducer with the highest possible frequency. Which piezoelectric crystal would you select? All right. Let's write out the equation. Remember, we don't have to do the math, but we do need an equation. We're going to find, once again, we're going to find frequency. Actually, frequency operating. Speed of sound over lambda. Remember, lambda, 2 times thickness is lambda. Lambda is the same thing. We want the highest frequency. Okay, so we want this arrow up. Highest frequency possible. Okay, well, there we go. We want then the highest speed of sound and the lowest wavelength. Right, so now all we have to do is just find, let me write that down really quickly. What's the lowest wavelength? Well, 2 times the thickness is wavelength. So in other words, I want the smallest thickness, right? Okay. Boom, boom, boom. Smallest thickness. Diameter. What can we do with that entire row of diameters? Don't need that information. Two elements. These two elements produce the same frequency. Diameter does not matter. Thickness matters. Okay. Let's see, letter D has certainly the best thickness. And let's see, we wanted a fast speed of sound. 4, 6, 5, 6. There you go. It's got to be D, the big D. All right. And then 303, the lowest possible frequency. Okay, well, so far, without looking at the answer, I'm thinking it's probably, 8 millimeters thick. Dang it. What is the answer? It is B. Oh, because I wrote that one wrong. That's why. I'm like, what? I don't know how I got that up there. I think in the book, B is it's just 302, 2 centimeter. Oh no, that was 2 centimeter diameter. It was 6. Okay. That was a little harder. That one you actually have to do the math for. This one's obvious. I'm sorry, 302 being D is obvious. 303 being B is a little bit less obvious. Yes, the thickness is telling us that that probably has the lowest frequency. But see, we have higher speeds of sound here and here. And so then you'd have to do, I think you'd have to do the math on that one, wouldn't you? No choice of diameter, they have to. Yeah, no, we know the diameter. Huh? Yeah, I don't know. He just kind of says, well, you know, obviously, I don't think that one's quite as obvious. Interesting. All right, well, that's it. I am done. And like I said, this one is how are we gonna count this one? Well, we'll see. We shall see.